All right. Welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have with us Dr. Peter Karkus, who is a research scientist at NVIDIA. There he's working on foundational questions around vehicle autonomy, and is part of Professor Marco Pavone's group. Something about Peter. So he did his PhD at the National University of Singapore, where he was advised by Professor David Su. And during that period, he also spent some time at MIT, CMU, Google, and DeepMind. So his research focuses on autonomous vehicles and embodied artificial intelligence, combining learning and structure and reasoning. And recently he has been working on neural networks, which can encode classic robot algorithms for localization, mapping, and planning. As you have seen, he's been for a while out there in the field, and he has received a number of awards. And today he's going to talk about differentiable robotics, compositional deep learning with differentiable algorithm networks. This is a topic that's very interesting for many reasons to the audience of Autonomy Talks, and that's why I'm very excited to introduce him and to give him the stage now.
All right. Yeah, thanks a lot for the kind introduction and also for inviting me. It's really an honor to be here. So yeah, today I will talk about differentiable robotics. This is a line of work I started during my PhD and that I continue to work on now at NVIDIA in the context of autonomous vehicles. Please feel free to kind of interrupt me anytime there is something I don't see you very well. So please say something if you want to, have a question or any other comment. Okay. Let me see if I can advance. Yeah. So let me very quickly acknowledge just my amazing collaborators who I was fortunate to work with on this research. Previously at NUS, MIT, and Google, and currently at NVIDIA within the Autonomous Vehicle Research Group led by Marco Pavone. So as most of you, probably very well aware, despite great progress in robotics and AI research, most of today's robots are still limited to operate in constrained environments like factories, separated from humans, and they are programmed to perform only a very, very narrow set of tasks. In the future, of course, we want robots to be capable of solving a large set of tasks in previously unknown and unstructured environments, closely interacting with humans. Now, going towards such kind of human-level robot intelligence, a central question is how to combine structure and reasoning with the ability to learn from experiences. And so to this end, in this talk, I will introduce differentiable algorithm networks, or DANs in short, which is a general architecture for designing scalable and compositional robot learning systems. So just to illustrate the generality of this framework, I'm showing you a kind of like a quick preview of some of the applications I will talk about later. These include visual localization, SLAM, planning for navigation, and autonomous driving. I want to start with a key idea. And the key idea is to implement robot algorithms in a differentiable kind of like neural programming framework where existing algorithms are essentially encoded into the structure of a neural network. For now, please ignore why we want to do this, and let's focus on how we can do it. And I promise that we will come back to the motivation soon. So all neural networks can be understood as computation graphs. They have some learnable parameters and some predefined operations. These differentiable algorithm networks are also computation graphs. The difference from a neural network is that these DANs have some fixed operations that together implement an existing algorithm. And this algorithm could be a control algorithm, a planner, a SLAM, or something like that. And then now the learned network weights can be then associated with a model. So for example, a dynamics function of a nonlinear dynamic system, or a reward function of a Markov decision process. And the only requirement that we have for this algorithm in a DAN is that all of its operations are differentiable, so that we can backpropagate gradients of the output with respect to learnable parameters, same as for neural networks. I assume that many of you have heard or are familiar with with computation graphs, but I still kind of want to go through a concrete example for a differentiable algorithm network, just to show you that there is really no magic here. Okay, my example is value iteration, which is a simple planning algorithm for Markov decision processes, MDPs. So assume we have an MDP with a discrete state, actions, transition model T, and the reward model R. This is the value iteration algorithm. It plans iteratively, computing action values, and then choosing the action with the highest value. So if these equations don't look familiar to you, don't worry about the details. They are really not important. The question is how we turn this algorithm into a computation graph. And here I'm kind of showing next steps, just the drawing these things, right? So first, let's look at the transition model and reward model. So these are T and R. And this in a discrete space, this T is just really a three-dimensional matrix or a tensor, and the R is a two-dimensional tensor. Now let's look at the first equation. Here, I just turned those operations that in the equation into a graph, right? So here we multiply the T with V. This is the element-wise product of a tensor and a vector along the appropriate axis. We have the sum over one dimension of this tensor. Then we multiply with a scalar gamma and add this with the R matrix. Okay, we can move on to the next equation. This is just another matrix operation along a particular axis of the tensor. Yeah. Then next we have the loop, which means we will be repeating this computation k times. So I'm just repeating this 2 times here. And then finally, we have this last line. This is an argmax along one axis of the Q tensor. That's it. Now we have this value iteration algorithm in a computation graph representation. So in this case, the learnable parameters could be entries of R and a T, or they could also be conditioned on some other input that is processed with a neural network component. In practice, all these operations are typically in auto differentiation libraries like TensorFlow or PyTorch. So we can kind of like simply code up these equations in PyTorch, and it will create exactly this kind of computation graph in the background. And as long as all operations are differentiable, PyTorch will be able to compute gradients for the learnable parameters by backpropagating through this computation. Now, of course, there's only one problem, which is an important one. In this case, the max operation. That this max operation is a discontinuous function, and there's a not differentiable. So that kind of brings me to the technical challenges of this. And the first obvious one is these non-differentiable operations. And I will now introduce a few high-level ideas on how we can kind of deal with them. But I will not go into details here unless we want to talk longer about it later. So for discontinuous functions like max, we can do a continuous relaxation that makes them differentiable approximately. So kind of like replacing max with softmax, indexing with soft indexing, and so on. Now, other type of problematic operations is sampling from a distribution. For Gaussian distributions, we can use the reparametrization trick. For discrete distribution, we can use Gumbel softmax. It kind of approximates discrete sampling with a weighted sum of possible values. Or straight-through estimation that only modifies the backward path to estimate gradients. And in some cases, we can use important sampling that reweights samples from a slightly modified distribution. An entirely different type of idea is that we can use implicit differentiation. If we have a computation block that has an iterative fixed point type output, we can derive gradients for the computation block analytically using the implicit function theorem. And now basically we'll have a different computation in the forward and backward passes. Many planning and optimization algorithms can be actually written in such fixed point iteration form. So this happens, for example, in ODE nets, if you are familiar with that, or differentiable modular predictive control. And then finally, we can actually always resort to approximating gradients for any non-differentiable computation or function with score function estimation. Now, of course, the issue here is that if we don't do anything, then our gradient estimates are going to have a very high variance, right? Yes. So there's another other type of challenge, and that is that the more computation we do, the larger the computation graph gets, which can be helped in some cases by efficiently parameterizing the model. So, for example, expressing value updates as a convolution layer. Another trick is to limit computation time during training and only increase it during test time. And the implicit gradients are also attractive here because they have different forward and backward passes. So we don't really need to store activations in the memory anymore. So all this, I have been talking about, how do we make the algorithms differentiable? And that we have these differentiable operations that pose a challenge and that we kind of have to address them somehow. So despite these technical challenges, differentiable variants of many classic robotic algorithms have been actually developed in the recent years. So we have differentiable algorithms for state estimation, like Kalman filters and particle filters. We have differentiable planners for MDPs, PoMDPs, graphs, and we have differentiable control algorithms and optimizers. So here I actually only listed a subset of this relevant work up to 2020. But the list is actually far from complete, of course, and have been growing ever since. So I'm sorry if I missed your favorite differentiable algorithm. Okay. So at this point, I hope that I kind of convinced you that it is possible to build in robot algorithms into neural network type representations. But the question is, why do we want to do this at all? Now, let's take a step back here and talk a bit about how we build robotic systems on a very high level. There are two main design principles: classic model-based design and kind of modern model-free design. Many of our robot systems today are actually still model-based. So in this framework, we can first build a model of the world and then use an algorithm to reason with that model and then choose robot actions based on this reasoning process. We can have, of course, multiple modules of models and algorithms. So typically in a robotic system, we would have a perception module, state estimation module, planning, and control, and others, right? These modules here are either specified by hand or learned independently. And this is also the setting that majority of control literature focuses on. I mentioned this because I know you guys work a lot on control as well. There we typically assume that a dynamics model and a cost function is identified first, right? And then we make some assumptions about the form of noise, and we are then concerned mainly with developing effective algorithms that find an optimal control sequence. Now, the benefit of this kind of model-based framework is that it's composable and it's interpretable. So what that means is that knowledge captured in these models can be recombined in different ways through the reasoning algorithms. So the problem, though, is that, well, first, it is inherently impossible to model the work perfectly, right? And the consequences of even small modeling errors can be amplified through the reasoning process. The second, even if we had a perfect model, we might still need infinite compute to find the optimal solution. So for both these reasons, we are always forced to make approximations, which eventually make the system brittle and require a lot of domain-specific engineering to make them work. Now, on the other side, we have the model-free framework, which, of course, brought unprecedented success in many domains where model-based approaches struggled for decades. Here, the entire system is represented as a single function, right? Typically parameterized by a neural network, and it is trained directly to optimize policy performance. Now, because of this end-to-end learning, the policy is robust in what it is trained for, and it improves with more data. But learned solutions tend to be kind of narrow because we lack priors to generalize from finite data. That this is important because if the task complexity increases, say combinatorially, right, the amount of data required to learn might easily blow up, right? Maybe we need 100x data, million-x data, or much more, right? So that's a challenge. Further, these neural networks lack interpretability and any formal guarantees, which are important in safety critical applications. So we have this kind of two sides, and seemingly they have very conflicting design principles. One key insight of this work is that actually these important design choices are orthogonal, and we could actually combine them, right? And so the left side actually makes a statement about how the policy is represented. It should be structured from modules so that knowledge can be recomposed in combinatorial number of ways. The right side makes a statement about how the policy should be learned. We want to learn end-to-end so that we can use data to directly improve the policy on the task distribution we care about. Now, if we look at them this way, the two sides talk about orthogonal things. And we can actually combine the two using the representation of the differentiable algorithm networks, right? So we already saw earlier that a computation graph can encode models and algorithms. So we get to retain the same structure as in the model-based system. But compared to the model-based architecture, the key difference is now we have the option to train models end-to-end, right? Backpropagating gradients through the algorithm. From the perspective of model-free learning, all we are doing here is we are choosing a particular type of neural network, right? That happens to encode these algorithmic components and model components. But otherwise, it's perfectly fine for us to understand the system just as a neural network, right? Everything remains the same, the way that we train it and use it. Okay. So to understand kind of like the benefits more, let's look at a visual navigation example. I will not have too much details on this, but briefly, in this domain, the robot receives a map with a goal here, but it doesn't know with its own location on the map, and they must use images from an onboard camera to localize on the map and then find the path to the goal, while also avoiding unexpected obstacles that are not shown on the map. So the environments here are, in this example, are generated randomly, random layouts and visual appearances. For training, we have 10,000 expert trajectories. And for testing, we use a separate set of previously unseen environments. And we tried in this domain, both a model-based system with modules for perception, state estimation, planning, and control, as well as a neural network policy with convolutional and LSTM layers that is trained end-to-end. They both achieve kind of some success in generalizing to new environments, but they're not perfect. Now, what we did then is that we used the exact same models and same algorithms as the modular approach on the left, all right? But we trained it end-to-end, just like the model-free approach on the right. And what we find is that the performance, at least in this domain, substantially improved compared to both. So let's kind of look at the two sides separately. Compared to model-free learning, this then has an additional structured prior that is useful to generalize in this domain, right? To understand the role of the structure, we tried actually to gradually relax the structure imposed by the algorithms, starting from our DAN network all the way to a simple RNN, training each variant end-to-end with the same expert data. And what we found is that as the structure weakens, the test time success rate decreases. And the benefit of this structure becomes much larger if we use larger environments that require more reasoning and make generalization harder. So the fact that structure is useful for generalization is, of course, not surprising at all. We often need structure, like for example, convolution we use for image classification. The interesting thing here is that what we see is that robot algorithms can also act as a useful kind of like inductive prior for learning. Now let's look at the other side. And here the difference is perhaps more surprising, because again, both approaches here have the exact same modules, same algorithms, same model parameterization. The only difference is how these models are trained, and it then trains these models end-to-end. So, okay, how does this end-to-end training help? Well, intuitively, instead of kind of like learning models to be accurate, we learn them to be useful. So we might even learn kind of like wrong models in that they're not accurately describing the world, but they were better with the concrete kind of approximate algorithm for the concrete task. So in this paper below that I have the reference for, there are actually a number of oftentimes surprising ways of how these wrong models can compensate for an algorithmic approximation. And I just want to show you one example. Here, the planning horizon of the past planner is purposefully set to be too short, 25 steps, which is less than the distance to the goal. So that's kind of like it's a terrible choice, but just for the sake of argument here, we are trying to find a path in a maze kind of environment with a planner that does not have sufficient horizon to even reach the goal. Now, if we run this planner, of course, with a ground truth transition model, as expected, it fails in all cases where the goal is further than the planning horizon. So now let's use the exact same planner in a DAN. Again, same short horizon. But now we learn the transition model using end-to-end demonstration data. And surprisingly, DAN solves almost all environments, even though it has the same short horizon planner. I can show you why this happens. So what you see in the left is the ground truth transition matrix for the turn right action. I mean, it's just a big matrix here with the 1 in the center, right? This basically correspond, each entry in this matrix corresponds to the probability of moving into a neighboring state, and you see that the turn right action has for turning right has a probability of 1. Right. Now, if we look at the model that's learned by DAN for the same action, the highest probability corresponds to turning and moving forward. Right, and this model is wrong because the turn right action in this domain will never result in forward motion. But you can see that this does shorten the required planning horizon, similarly to how like a macro action would. So essentially, this DAN learned a wrong transition model that nevertheless works better with this imperfect planner because it invents its own macro actions for the purpose of planning. Right, and that this was like one example, but that we found a number of different ways where similar things can happen. So I just very quickly mention a few. So for example, when our transition model didn't capture obstacles, our DAN could compensate this by inflating collision penalties. In a partially observable planning problem, the planner didn't account for information gathering, but DAN could compensate this by basically reward shaping, learning rewards that explicitly incentivize information gathering action. Mistakes in the perception module here often led to poor irreversible actions. By relaxing the perception interface, DAN basically learned to encode confidence in the perception output. And so subsequent modules learned to use this confidence, and so they could avoid these irreversible decisions. So basically what we can see is that fixing approximations can happen in many ways. And while these fixes sound kind of like hacks, especially in that type of example I showed you, like reward shaping, dropping low confidence predictions, and so on, I want to point out that these kind of hacks are actually very, very common in robotics practice, right? The interesting thing here, in my opinion, is that we didn't do this by hand. We didn't introduce these hacks by hand, but rather these hacks emerged from end-to-end learning instead. Right. So to summarize my points so far,
Peter, sorry to interrupt you.
Yes.
Can you hear me? I think there was a good point to ask a question that's in the chat.
Okay.
Which is from Ariant. He asks, how much interpretability do we retain using the DAN network?
Yes, a great question. So I think it depends. How much we want to retain, right, and how much constraints we put on these models. So in some sense you can kind of relax more and more of the model constraints, and you sacrifice more of your interpretability, right? But compared to the alternative, that's say like the thing in the right side, a fully neural network type architecture has almost near zero interpretability. Right, and the thing on the left has like say like the maximum interpretability we can get, and so in some sense we can kind of fuse between the two. We sacrifice some of the interpretability for the sake of kind of improving the overall system. At least that's a kind of like the way I think about it. It's of course also possible in some cases that retain the same amount of interpretability, but you just kind of train the different modules to be behaving better together. And we will have some examples in the end for autonomous driving where we don't lose any interpretability, yet we improve overall performance. Does that make sense?
Yes. If I may also follow up, if you don't mind, do we also retain the interfaces between the models, for example?
Yes. So yeah, great question. I mean, we can, or we can choose not to. All right. And so if we retain the interfaces, then we understand more. Like for example, in this previous example, here all the interface remained exactly the same, and even the model structure remained the same. It's really just the probability values for that in that transition matrix. And so this way you can, for example, this is, I don't know, it's less interpretable, I guess, than the original one, but it's still kind of interpretable, right? I could see that, oh yeah, like it really like turned and moved forward. This is what it thinks in its head when it's turning. And so, yeah, sorry. And for the interfaces, indeed, we could also then relax them. So at that, again, we can give up a little bit of interpretability, but potentially we can, communicate much more between modules. And we did that a little bit with in this navigation case with the perception side. So we asked the perception module we relaxed kind of like the interface of the detected obstacles, and this allowed it to communicate this uncertainty in this learned interface. But we could no longer tell exactly what it is detecting.
Yeah, very nice. Thank you.
Okay, yeah, thanks a lot for the question. I think that was very good. So, yeah, okay. So basically, we can understand this, then from both sides. We can understand this a model-based approach. Only thing is that now we change the learning objective, right? This task-oriented learning can be beneficial because it can increase robustness against imperfections in our modeling assumptions, and we can learn new representations, right, and interfaces between the modules. The price we pay for this, exactly as we are just discussing, is that we lose some of the interpretability. We can also think of them as an end-to-end model-free learning approach, only that now our network has some special task-specific structure. And what we gain by this structure compared to model-free learning is better generalization, better interpretability. The price we pay for it is that we require some more domain knowledge, and also as with using any kind of prior, we are limiting the maximum achievable performance in that limit, right, with infinite data. Okay, and yeah, this is also kind of reflecting on the same question. So more broadly, we can think of a dance as something that opens up the entire design spectrum between fully model-based algorithmic architectures and end-to-end neural network type architectures. We no longer need to choose one or the other. We are able to blend them in arbitrary ways, because we can reason about both architectures in a single conceptual framework where algorithms and neural networks are both just different instances of differentiable computation graph blocks. Okay. So if I was kind of listening to myself here, I think I would think that, okay, this kind of sounds like a nice and neat idea, but does this, actually happen in practice? Does it actually work for any domain like we actually, care about? So now that brings me to some of these applications. As I mentioned earlier, I picked 4 robotic domains as examples from my earlier works. But in the interest of time, I will only say a few words about these first 3 and spend most of the remaining time on the 4th, autonomous driving. Okay, so in the first example, a robot has to localize in a previously unseen environment, given a floor map like this, and first-person RGB images. The differentiable algorithm network here encodes a differentiable particle filter algorithm, along with learned transition and observation models that's normally required for the particle filter. And this particle filter network works by basically maintaining a distribution over states, here represented as a set of particles. They are in gray here. And now I play the video. As you will see, as new observation arrives, these particles are updated using a learn transition and observation models. And what you see here in this example is that after training, the filter network can maintain a multimodal distribution over possible poses for a while. And then the particles converge to the correct mode and track this robot pose nicely. Okay, and now this next application is SLAM, this differentiable SLAM net. In substance extends the work on the particle filters to a full SLAM setting. Here the robot has to simultaneously build a map and localize from visual sensors in previously unseen environments. And here I'm showing some experimental results from the habitat simulator that uses real-world image data. And here differentiable SLAM net performed actually significantly better than both an alternative learn solution and maybe more surprisingly, even better than the ORP SLAM, which is a very popular SLAM algorithm. The reason for that is that ORP SLAM struggles really in this setting because of the noise and the low frame rate, whereas our learn network could kind of learn how to handle that. Also, we kind of connected this SLAM network to a planning algorithm for navigation, and here SLAMnet also achieved the top score in the Habitat Challenge 2020, I believe, on the online leaderboard at the time. Okay, then this Dan algorithm, or the navigation example I showed you before, was also actually deployed on a Boston Dynamics Spot robot to navigate buildings in our university campus back in Singapore. And these Dan modules were trained in the habitat simulator and then transferred directly to the real robot. And in this scenario, the robot can avoid arbitrary clutter, chairs and other things that it has certainly not seen during training. Okay, so as I mentioned before, of course, our group at NVIDIA focuses on autonomous vehicles, AVs. So I want to spend more time on this application. One of the large research trusts in our group focuses on developing next generation AV stacks that scale kind of both with labeled and unlabeled data. This works to largely build on the idea of differentiable algorithm networks. Is there any question kind of maybe here, because just so that before we move on to AVs? If not, then let me continue. So we can kind of rephrase this question that we look at a group. How do we make modular AV stacks scale with data? And so in vehicle autonomy, similar to the rest of robotics, there are two main architectures that are being used today. On the one hand, modular architectures, right? They typically comprise of independently trained modules for example, for detection, tracking, prediction, planning, and control. And this is the approach that many AV companies adopt because of key advantages such as interpretability and reusability. However, this architecture introduces information bottlenecks between modules and give rise to integration challenges. On the other end of the spectrum, again, we have end-to-end architectures which directly link perception to control, typically through a neural network, and only implicitly encode key capabilities like agent prediction. As key advantages, the end-to-end architecture removes information bottlenecks, and one could argue that they might achieve a level of optimality unattainable by modular architectures, which are based on a rigid modular decomposition. But among other things, it is very difficult to make any formal safety claims of such architectures. So a natural question is then whether we can get the best of the both worlds in terms of architecture design. And to this purpose, we are developing modular yet end-to-end differentiable AV stacks that keep the main modules of traditional AV stack, but at the same time train these modules jointly end-to-end from data. Right? So you can think about this. Essentially, we are implementing the stack as a differentiable algorithm network. That is, the stack is now a single differentiable computation graph, and the differentiable representation then allows us to propagate gradients through both neural network components as well as fixed computation blocks. For example, like a classic controller or planner algorithms. And this way, we can perform gradient-based learning end-to-end, essentially improving upstream modules directly for downstream tasks. Right. And to make the ideas complete, let's focus on the motion prediction, planning, and control modules. We choose this, as an interesting setting, not only given the importance of these tasks, but also because this algorithmic pipeline comprises of both typically data-driven components like the agent prediction and the handcrafted algorithms, typically planners and controllers. These are normally not differentiable. So our stack that we are looking at here has a predictor, a neural network that predicts a distribution over future trajectories of traffic agents, given the history of these agent trajectories. Then it has a planner that samples, in this case, it samples ego trajectory candidates and selects the lowest cost candidate based on predictions and a handcrafted cost function. And then finally, we have a model predictive controller that optimizes the trajectory further with an iterative LQR algorithm. So in a conventional stack, the predictor is usually trained to minimize prediction error, and the planner and the controller are typically handcrafted. Now, what we did in the diff stack is that we first make the planner and controller differentiable. So we do this in the planner by approximating the argmin there with sampling, and in the controller we use a differentiable MPC from prior work. So what we can do now is to backpropagate losses through the control and planning algorithms, and train the prediction model for not only the prediction objective, but also for the downstream planning objectives. Okay, so we benchmarked the two methods on this is standard new scene driving data set. We compared two architectures. This is a standard stack that trains only the prediction model to minimize prediction error, how it is normally done. And the diff stack that trains, again, only the prediction model, but it trains that for a combination of prediction, planning, and control losses. And we will measure two things. So we measure prediction performance through the average displacement error, ADE, and planning performance through the average cost of ego trajectories. And here, because the absolute cost values are hard to interpret, we are presenting a cost as a percentage difference compared to an oracle that plans with perfect ground truth prediction knowledge about the future. So lower is better. Now, while the two stacks perform similarly in terms of prediction error, diff stack achieves a substantially better plans, reducing this average cost difference to the oracle from 29% to 17%. It's important again to highlight that the two stacks perform the same computation at inference time. The only difference is that in this diff stack we train the predictor to be more useful for planning and control. Okay, and what's the reason for this improvement? Well, the key underlying reason is that, of course, not all prediction errors are born equal. So, on the left example here, it's clearly much more important to accurately predict the behavior of this pedestrian trying to cross in front of the ego vehicle compared to this other car that's far away. And on the right example, this is somewhat less trivial. We show two metrically equal prediction errors that have very different consequences on the plan. So if we incorrectly predict that there's a vehicle will stop 1 meter, 1 meter before the stop line, it doesn't really have a lot of effect on planning. But if we incorrectly predict that this vehicle will, stop 1 meter after the stop line and enter the intersection, that may trigger then a dangerous, evasive maneuver from the ego vehicle. So these two errors are, exactly the same in terms of a prediction metric like ADE, but they're very different in their impact on the plan. So in diff stack, we train the predictor to be aware of these consequences on prediction and planning. And indeed, in our experiments, we found concrete examples where the diff stack predictor yielded less spurious predictions, which would otherwise be critical for the planner. This is a little bit hard to see, but here we are showing the predictions in orange and the ego planning in red. And in the left side, the standard stack basically predicted here an unlikely lane intrusion, causing the planner to swerve. And the diff stack learned more reasonable predictions that consider the presence of this ego vehicle, and so the resulting motion plans stay well within the lane boundaries. And so on the right side, the standard stack here incorrectly predicts that a vehicle would basically collide into the ego from behind. And this stack, assigned a lower probability to this event, and so it produced a more reasonable motion plan that doesn't enter into the intersection. It's a little bit difficult to see them in these visualizations, but believe me that this is what's happening. Okay. Now, of course, these results were just a first step. Our long-term vision with this is to make entire AV stacks differentiable, including perception modules like detection and tracking. And this unlocks various new opportunities. So, of course, we could just jointly optimize across the entire stack, and this is what I have been what I share some promising initial results for. But beyond that, we also have opportunities for learned representations and interfaces between modules that could, for example, propagate uncertainties across the entire stack. One concrete idea we are working on is learning new occupancy representations in a self-supervised fashion that I will, if I have time, I will talk about it soon. Differentiable stacks may also play important role in other topics in AV research. For adversarial robustness, we may develop new type of attacks that target a particular module, yet directly optimized for triggering poor overall behavior. For evaluation metrics, we may develop new task-oriented metrics with this. And we may fully leverage emerging AV simulation technologies by generating massive amounts of closed-loop training data. So the reason why, again, we are kind of excited about this differentiable stack is not only that we necessarily want to keep all current model-based algorithmic modules in the stack, but because through this differentiable computation graphs, we have a unified representation of both algorithmic and neural network components. And so, this again opens up the design space between model-based modular architectures and entirely monolithic end-to-end neural network architectures. So there's one more topic I wanted to share. I don't know if we stand on time.
Yes, we have time. Yeah, go ahead.
Okay. I think this will be another, 5 minutes. Yeah. So this is another work that is going on at NVIDIA that I'm particularly excited about. So far, I've been talking about joint training of modular stacks with some form of supervised data. But labeling data for autonomous driving can be very expensive. We have seen incredible success of foundation models recently in generative AI, both for image generation and language models, that essentially learn a very powerful representation from massive amounts of unlabeled data. So we are now looking at the potentials of unsupervised representation learning in modular AV stacks as well. Why do we need learned interfaces? Well, the most common interface to connect perception and planning is bounding boxes. And now perception models output a discrete bounding box set, followed by a tracker that associates bounding boxes across time. This paradigm is used by almost every autonomous driving pipeline. The limitation, however, is first that the detectors struggle with rare objects not represented well in the data set. Two, the arbitrary shapes are hard to express as bounding boxes. So think of like a protruding crane above the road. And these bounding boxes contain very little information compared to what is represented in the sensors. So an interesting alternative we are currently looking at is to model the environments through occupancy voxels with some learned semantic representations. These occupancy voxels can model arbitrary objects, right, including objects not in the dataset, and it can provide more accurate geometry, leading to better occlusion reasoning, planning, and so on. So we argue that these voxels will these voxels can be augmented with learned features beyond simple occupancy, and we can retain this way much more useful information from the sensors. So let's look at how we learn this occupancy representation at the moment. The core of our proposed method is a generalizable neural rendering. So neural rendering originated from computer graphics. This provides a convenient way to link 3D representations like voxels to 2D images that we can see. The core idea of this neural rendering, or specifically volumetric rendering, is to represent the scene with 3D occupancy and color fields, and then a neural network can query this 3D representation and differentiably render pixels by aggregating color information along each rendering ray. Okay, and so we want to leverage this volumetric rendering to self-supervise the learned 3D representation. And our method inputs multi-view images, passes them through image encoders, like transformers. These the encoded 2D features are then lifted to 3D with implicit depth estimation. And then finally, these 3D feature voxels are rendered by volumetric rendering to generate the original images for the current time step and or future time steps. Now, a very strong advantage here, and the reason why this representation can scale, in our opinion, is that we can learn it from self-supervision, only using the sequences of sensor data. Additionally, we can also distill pre-trained foundation model features to these 3D feature voxels, for example, from Clip or Dino or things like that. And here are some very preliminary results of our learned interfaces. So we can generate novel views based on a new camera trajectory. Most importantly, here the learned representations lead to consistent depths and semantics across time, as shown in this video. The first one is the image, second is depth, the third is some features. In addition, thanks to here in this case, we use a clip feature, the model also enables open vocabulary scene manipulation. So for example, we can query the 3D representation with language prompt to remove backgrounds and only keep cars, right? That's like the second row. This is done basically by finding the corresponding voxels to text features with feature space nearest neighbor search. So we are now working on building planning architectures and even whole autonomous driving pipelines on top of these learned representations. And we envision this representation can enable autonomous driving in arbitrary domains without heavily relying on heavy human annotations. So this is all the core content I wanted to share. Let me summarize the key points of this talk. So if you remember anything, I hope it will be the fact that we can build robot algorithms, including control algorithms, into neural networks. And then in this manner, this then framework can combine the modularity principle with task-oriented learning. So we can preserve our interpretable modular architecture, potentially with the safety guarantees, and at the same time train and modules jointly from data. Then we looked at a number of applications in robotics, including autonomous driving, and I shared some of our ongoing and future work in this area, how to make existing modular stacks scale with both supervised and unsupervised data. And then one shameless plug for the end, we are hiring. So NVIDIA research group is mainly in Santa Clara, but we have presence in various countries, including Zurich. So I myself in Zurich. And we have open positions both for full-time research scientists, as well as research internships that are typically, for senior PhD students, 3 months roughly, typically resulting in a publication. So if you are interested, then please reach out to me. And with that, I would like to, thank you for your attention, and very happy to take any questions.
Thank you very much, Peter, for the great talk. Let's open now the stage for questions. You can either ask directly by raising your hand and I call you, or write in the chat and I can read the question for you. We have some questions already in the chat that I can start asking. Okay. So Angel Aguilar asks, how does the diff stack approach compare to end-to-end learning in terms of training times? And from his experience, the differentiable MPC from Amos et al. Needs to solve optimizations at training times. Are you able to leverage GPU power for training these pipelines?
Yes, a great question. Yeah, I guess in this talk, I didn't really get into too much of these difficulties. So indeed, it is kind of harder in terms of training time compared to, so basically by imposing structure in this end-to-end architecture compared to a neural net, standard neural net, we are kind of making the optimization harder itself. So that includes training time, but also includes kind of like a stability of training. So we can think about this optimization landscape that we are trying to optimize over with stochastic gradient descent is much harder, right? Because like neural networks typically kind of easy to optimize because they are very over-parameterized. We are kind of restricting that in some way. So this becomes a harder optimization problem. So that's kind of like a difficulty, right? To some maybe, I mean, for me at least, compared to what in the beginning, I was kind of skeptical how we'll be able to scale this, but we were able to actually scale this quite a lot. So like for example, in the navigation planner, we have been planning up to like 100 iterations, a lot of particles in a particle filter. So yeah. It's slower, but we hope that we can scale it. And of course, it also kind of, if you're working on like optimizers, then I think this is a very interesting area to kind of develop optimization algorithms that handle better this difficult optimization landscape beyond just Adam. Right.
Perfect. Thank you, Peter. So the next question is, in your proposed approaches, there is always an information bottleneck between modules. That's something you discussed before. Mm-hmm. Is this not a problem? And if it is, how do you think you can overcome it while maintaining some interpretability going forward?
All right. Yeah. So I mean, it can be a problem. It can be not a problem. So I guess like in the interfaces or any of the algorithmic computation, I tend to think about them as some form of knowledge we are injecting into the system, right? So ideally we want to have as a little prior in the system as possible. But with that, we will need a lot of data to train. And when I say lot, this is kind of like the unknown question about if we think about like a general robot intelligence, is that amount of data we need like for a human level intelligent robot? Is it like 10x what we have? Then maybe it's fine. But if it's 10 to the power of 6, 8, 10, then the number of atoms in the universe will be more than like less than the number of data points we need. That's a problem. So in that sense, we will also always need some form of inductive biases. And so these interfaces and algorithmic components, in my mind, are options that we can build in as inductive biases. Yeah, I don't know if that answers the question.
Yeah, please. Okay, yeah. Great. Okay. Great, yeah, so there is a third question, which from Jonathan, who asks, as far as I understand, the then approach is more interpretable than the end-to-end approach. But as you have said, in the individual modules in the stack are useful to solve the task and not necessarily accurate. So how can you establish safety guarantees for these systems?
I see. Yeah. Yes, indeed. So if we were, I guess, if we wanted to have serious safety guarantees, then I think the only really option, the true option we have, is to very much restrict the space of the model space and the output space, right? And we have to make those intermediate representations interpretable if we talk about really formal guarantees. Now, how important these formal guarantees are in practice, when anyway most of our perception comes from these learned networks and all that, is a different question. But so for serious guarantees, I think that's the only option. Now, if we are also kind of happy to have some interpretability or some formal thing we can state about the network, then we have much more options, right? We can start to relax something. So, for example, you could have like alternative paths that use a detection, object detectors, but also communicates the things directly from the sensor. And so you can kind of like look at what the network understands intermediately, but we also allow it to kind of shortcut that representation when it's needed. Yeah, I hope that.
Yeah, I think, Jonathan, if you have a follow-up, please write in the chat. And the next question is from Eugene, who asks a related question, I guess. So the question is, you mentioned modularity and generalizability, but you also show that this method usually is applied to task-driven settings. So how are you able to generalize for different tasks? Can you reuse all the training you've done?
Yes, yeah, great point. Again, I think my answer will be very similar. So it depends. Of course, some of this might not be reusable, and in fact, some of this joint training, what it is useful is that you have these components and you kind of like fit them to the task you really want to solve, right? A task meaning like a distribution of things that you care about. So in some sense, it kind of like reduces the reusability. But I think in terms of the reusable things, though, here are definitely the things that we know about robotics, right? The algorithms we know, the model structures that we know, like for example, like I haven't really shown these concrete results, but these domains that we have been looking at, like visual localization, SLAM, or navigation. We know a lot about them, right? About the algorithms that are useful for them. It's just that the assumptions we require for them are introduce some imperfections, and the compositions are imperfect. So we can use data to kind of fix them up in that sense. So why I'm saying this, because I'm saying kind of like the modules, the algorithms themselves could be very much reusable. While maybe the things that we learned for that task and adapted to that task are less so.
Okay, thank you. Then there is another question, this one from Michael Schwegel. I guess this one is at a higher level. You mentioned learned interfaces. And do you have a plan on how to achieve this, since the algorithmic blocks you defined before had their interfaces defined intrinsically, whereas the networks might suffer from the same problems as common neural networks?
Yes, that's true. Well, I mean, I guess again, in my mind, is a little bit about the spectrum, right? So indeed, if we throw away an interface in the larger system, that means that with that there we can lose some of this interpretability and generalization benefits. But that doesn't mean that other components cannot have them. So, for example, again, I haven't really showed this work, but the particle filters, we also managed to use them in a very almost model-free settings, right? Where everything, the particle state representation, the dynamics, observation model, everything was learned. So it was very similar to like a neural network kind of thing. The only inductive bias it had was about this reasoning about potential underlying states and the filtering them discriminatively, right? But everything was very latent, and that also showed that in various domains that substantial benefits that require this reasoning about partially observable underlying states. So I guess what I want to say overall is that injecting these algorithmic computation blocks can be very useful in themselves, right? We kind of like, we don't want the network to learn how to search a graph. We know how to search a graph. We can build that in, and then everything else, what the graph should be, what the weights are, that we can learn, right? And so that's where kind of how I see this, and the same for this the last work that I shared in for foundation AV foundation models. Again, kind of like we can think about it the same way that you learn this representation from unsupervised data, and then we want to kind of have this differentiable pipeline after it, so to make that representation kind of useful for what we will be using it for. That's to drive, as opposed to like render nice images. which that's the only thing I showed you. We render nice images, but doesn't mean really that they're going to be useful for driving. So that's kind of like how I see the role of these learned representations and interfaces within these bands. I hope that makes sense.
Nice. Yes, Michael says, okay, thanks. So I guess this answers the question. Are there any other questions? I don't see them in the chat, but maybe somebody wants to ask something directly. Okay, doesn't seem so. Thank you very much, Peter, for the great talk. Also follow up to Peter in case you want to be considered for the many positions they have open. I think this is a great opportunity.
Yes, indeed. Thanks a lot for listening. Yeah, sorry I spoke very long, but hope that it was.
Thank you. It was really appreciated. And we'll follow up with once the video has been edited.
Yeah, sure. Thank you.
All right.
Thanks.
Thank you. Take care. See you all next week for the next talk. Bye-bye.